Hi class, today we are finishing chapter 6 with 6.8. This is the shapes and polarities of molecules. So we've already discussed polarity and non-polarity in the previous section. And what we did is we looked at bonds, one bond on a molecule to determine if it was polar or non-polar. Now we're going to look at the whole molecule and how that polarity affects the shape of molecules. So let's take a look here. First, we understand Lewis structure. Lewis structure is how we draw with electron dots, and then we create dashes to make it look cleaner. We can see everything that's going on. Then we have it as a tetrahedral electron group geometry. I'm going to go and explain more of this as we go through this. So I don't expect you to fully understand what you're looking at right now. Then we can change this into, by removing this square, and we can determine what the angles of all the bonds are. And this is where the shapes of the molecules comes in. If we're not able to draw it like this, then we draw it with wedge dash notation. If you plan to go into organic chemistry, you will draw everything like this. I'm going to explain how this is. This HCH is in the plane. If you're looking at this on a screen of a laptop tablet, that's in the screen of the tablet. This dashed wedge is facing directly outward in back. And this dark wedge is facing directly at your face. So one is pointing back, one is pointing forward, and then the HCH is in the plane of the tablet. That's kind of like a 3D visual to get you to understand how this actually looks. And these are not flat molecules the way that the Lewis structure is drawn. So what we're going to do here is determine the polarity of the whole molecule. And that comes with VSEPR, which is valence shell electron pair repulsion theory, VSEPR. It describes the orientation of electron groups around a central atom. It states that electron groups are arranged as far apart as possible around the central atom. This is to remove repulsion because we're dealing with electrons here. And like a magnet, if you put two identical sites, they will repulse. They will force themselves away from each other, and that does not make a stable molecule. So we want these as far apart as possible, these bonds, to keep it at its lowest energy. Remember, chemistry is all about the lowest energy is the most stable compound. States that the specific shape of a molecule is determined by the number of atoms attached to the central atom. So I'm going to go through all the shapes here. First, an electron group can be an electron pair, a lone pair, a single unpaired electron, a double bond, triple bond on the atom. So I like to call it attachments because that gives you a better idea of what you're looking at. So when we're looking at attachments, we're not concerned with what type of attachment it is at this point, just that something's touching the central atom. And then we will expand on that after. Excuse me. So we have carbon dioxide here. Carbon dioxide has two bonding electron groups. So we're not looking at the center atom. This is a central atom with two electron groups. So we have two electron groups attached to it here. The repulsion is minimized by placing them far apart as possible, and that is at 180 degree. So based on this would be a linear electron group geometry. So remember, we're looking at electron group as an attachment. Linear electron group geometry. The shape with two electron groups around central atom linear. It does not matter that it has a single, double, or triple bonds. And carbon dioxide here has, sorry, my throat is all of a sudden starting to act up when I'm talking, has double bonds, but we still count it as one attachment. We're one electron group here, one electron group here. We're not at this point interested in what type of bond it is. It's just an electron group. Now, we're going to look at a central atom with three electron groups around it. We have formaldehyde, which has carbon in the center, two hydrogens, and a double bonded oxygen. So this has three electron groups around it. First, you would draw the Lewis structure, and then you would try to determine the shape of it. So we have three, doesn't matter if it's single, double bond, triple bond, it's just three electron groups around it. This gives us a trigonal planar shape. There's a chart that I'm going to show later on, and that's where these shapes are showing, but I want to go through this first. It makes it easier to understand the chart. So you're not going to just have to memorize this. You would be given a chart to determine what it is you're looking at. But I will tell you that you might be given something of a molecule like this, and you will have to put it together in the Lewis structure, determine the shape, and then write the angles out. So this has a trigonal planar shape. It's plane. It's kind of all flat in a plane of paper, and they're all 120 degrees difference from each other. That is the lowest energy to keep these electrons from having a strong repulsion from each other. Now we have central atom with 3 electron groups again, but these are not all bonded atoms. So in this molecule, we have SO2, and we have a single bond, and we have, so here's a single bond, a double bond, and a lone pair. And with this, it kind of does change a little bit. So what we're looking at here is the repulsion is minimized by placing the 3 electron groups as far as possible. So we would draw the Lewis structure. We would determine the electron group geometry. Now, electron group only depends on how many are touching the central atom, not what type is touching. Actually, that's not right. Excuse me. Yes, it is. This is the one I'm thinking of. We have 3 electron groups. It's a lone pair, but it still has an attachment to the central atom. So it's 1, 2, 3. So this is called trigonal planar electron group geometry. That is very similar to what you see here, trigonal planar. However, when you actually look at the compound and realize that you only have 2 bonded atoms and not 3 bonded atoms that you see here, there's another shape that's also going to be called. So that's going to be called bent. And that's because this lone pair that you don't see here, and that's some of the problem when you see some of these molecules, they don't always draw the lone pairs in. We look only at the bonded atoms to determine the actual shape of what's going on, even though there's a lone pair here. So there's 120 degrees here, and this is called bent. And you don't see the lone pair here, but this would be 120 and then a lone pair. And what this is not actually saying is lone pairs take up a lot of electron density. So think of this as an electron cloud. This would be a huge cloud of electron density around this part of the atom, and that pushes these bonds closer to each other and further away from the lone pair, which actually takes up more space. But again, when we look at the actual shape of it, it's bent. Electron group geometry, all attachments, 3. But when we look at the actual molecule, we don't consider the lone pair. We only look at bonded atoms, and that gives us a bent shape. And here's a key, and it's in your book, and I copied it exactly as it says in your book. Central atoms that has more electron groups than bonded atoms, the shape and the electron groups geometry have different names. This is a perfect example of it. In the ones that I've showed here, the shape and the geometry have been the same because they're all bonded atoms. Now we're dealing with the lone pair, so that means that we have 3 electron groups, but only 2 bonded atoms. So the sentence says if you have more, and it has more electron groups, which we do, we have 3, than bonded atoms. The names are going to be different for these. So that means a lone pair. If you have a lone pair involved, the name's going to be different for electron group and shape. Central atoms with 4 electron groups. This is going to have the same name because we have same all bonded atoms here. So we have 4 electron groups attached to the central atom. 1, 2, 3, 4. You would draw this out. And then you determine what kind of electron group geometry is going on. You would have a chart, and we're going to look at that chart later after we get through all of these. And it's also going to tell you the angle of all. This is 109, this is 109, this is 109. And then you're never going to have to draw it this way. I don't think the book, as from what I can tell, they're not requiring this. And if they do, I would go over this again if anybody needed help. But this is more 3D to allow you to see that it's not flat like this. So what this means, again, the C and the 2 H's are in the plane of your laptop screen. And this dashed H is directly shooting out behind it. And the H here with the dark wedge is shooting directly at your face. If the laptop, your screen is directly in front of your face. So that gives a 3D to give you an idea of what this looks like. Central atom with 4 electron groups. Again, another 4 groups, but this time we have a lone pair, which means that the shape and electron group geometry not going to be the same. We have a nitrogen, and we have 3 hydrogens and a lone pair. What this is not saying again is that the lone pair has a huge electron cloud around it, and it forces the other bonds away from it. It takes up the most space. So when we look at electron group geometry, we count all the attachments. 1, 2, 3, 4. We have 4 attachments, so this is going to have a tetrahedral based on those 4 attachments. However, now we look at bonded atoms, and there's 1, 2, 3. So based on the fact that there's 4 electron groups, but only 3 bonded, it's going to tell us that this is trigonal pyramidal, which, as you can see, kind of looks like a pyramid. And the lone pair aren't drawn on this, so you don't see that that's actually what's happening, is that there's a lone pair pushing these down away from it. Excuse me. And if we want to go through this one, the same thing. The N and the H are in the screen. The H here is shooting directly backwards out of the screen, the back of your laptop, and this H is going directly in your face to give a 3D kind of idea about it. Central atoms with 4 electron groups. So here we have 2 lone pair now, and we're dealing with water. And the shape of this basically determines how water has all the properties it does. And I'll go into that in another section. But if you're not understanding why we're studying shapes, shapes really do determine the properties of these compounds. And water, the whole reason why water, I mean, there's many reasons why water is what it is, but compared to other molar masses, it would be a gas. It should be a gas, but because of its bent geometry, it has certain properties that allow it to be a liquid at room temperature when everything else in its molar mass is a gas. In a molecule of water, we have 4 electron groups. There's the chart. 1, 2, 3, 4. Now we have 4 electron groups. So if we look at the chart, we'll do it now. Excuse me. Here's the chart, and I'll break it down. So here we have 4 electron groups. So let's take a look at where 4 electron groups are. Here we go down, and there's 3 sections of 4 electron groups. They're all tetrahedral. So 4 electron groups, tetrahedral. Okay, now let's go back up. So it gives us a tetrahedral kind of, if you were looking, as of right now, we haven't gone further in it, it kind of looks like this. Now the next thing is we're going to look at the bonded atoms. So we're no longer looking at the whole electron groups, we're looking at the bonded atoms. And what you don't see here is that the 2 lone pair push these towards the bottom. So they are forced together while there's 2 lone pairs. So there's a huge cloud here separating each other. So there's like a petal, think of like a flower petal, and it takes up a lot of space. And these push these down. So now let's take a look. We have 4 electron groups, and we have 2 bonded, and we also have 2 lone pair. That tells us that this is a 109-degree angle between the bonds, and it is a bent formation. Water is an example, which is what exactly we're looking at, and it looks like this. And that's exactly what we have here. These colored balls, they are very specific to what, so oxygen is red, hydrogens are white, and you can buy these geometry sets to actually put these together, and you can see them. I don't know, maybe you can find something cheap online. If you're having a hard time understanding how to do this, you can put them together, and they're meant to the whole modeling set is exactly meant for this, the shapes of it, so to understand it. If we were in person, there would probably be in a lab that you would do this. Okay, so here is the chart that I was working off of. Electron groups is attachments. Doesn't matter what type, doesn't matter what kind. They're attachments to the central atom. So you're not counting the central atom, you're counting the attachments to the central atom. Then there's the name for the electron group geometry. And you need to make sure you understand what electron group geometry means compared to molecular shape. So here is the name of the electron group geometry. Now we're looking at bonded atoms and lone pairs. So now they're being separated out. Now, if you have bonded atoms, then the 2 will remain the same. So we have 2 electron groups, 2 bonded atoms, 0 lone pair, linear, linear. If we go down to where there's zeros, electron group here 3, trigonal planar, bonded atoms 3, no lone pairs, trigonal planar. So the names match on these. Go down to tetrahedral, 4 electron groups, tetrahedral, 4 bonded atoms, 0 lone pair, tetrahedral. So the molecular shape and the electron geometry will match. The molecular shape does not count lone pairs. It only counts bonded atoms. And then as you see, as you start getting with lone pairs, then you see that the names will not match, and even within themselves. So you can see that this is 3 bonded and 1 lone pair. It's trigonal pyramidal. This is 2 and 2, and it's bent. So even amongst themselves, the lone pair can also dictate what is happening. Okay, so now we're going to get into predicting the shape. This is not an easy portion of this chapter. I've tried to put it together in a way that makes sense, and it still may not. You may have to read this. You may have to go over this a lot. This is not an easy section. That's why it's the last section too. But it builds, everything in chemistry builds upon itself. So hopefully this makes sense. Predict the shape of a molecule of H2S. So you're given H2S, and you would have to draw it out. How do you do that? Well, you figure out the valence electrons. So we have 2 for 2 hydrogens, and we have 6 for sulfur. So we have 8 electrons to work with here. Hydrogens only take 2, so we have a duet and a duet. It's done. But sulfur needs an octet. 2, 4, 6, 8. It does. So we're good with that. Now we need to arrange it. So you would just draw it, and you would try to draw it in a way that you think it doesn't get the repulsion. Remember, lone pairs take up a lot of space. So you think that this would look this way, but the problem is this is flat, and we have to draw it more as a 3D to give it a better understanding of what's happening. So to minimize repulsions, electron groups have a tetrahedral arrangement. So if we look back, this is 4 electron groups, but 2 lone pair. So we have 4 electron groups. So we go here, 2 lone pair, and 2 bonded. So this is going to be angles of 109, and it's bent. So the lone pairs are going to be here and here, and we're going to draw this as a bent molecule. And that's what you see here. You see it drawn as a bent, and this is a 109-degree angle. Here is what the giving you a visual of what these look like. So this is 2 atoms and it's linear. This is 3 atoms and it's linear. You can see that they are spread out. The greens are the lone pair to give you an idea of what some of these look like. Okay. So state the number of electron groups and lone pairs and use the Vesper theory. That is what I just covered. The chart, all of that, the shapes are Vesper theory. To determine the shape of the following molecules or ions as tetrahedral, trigonal pyramidal, or bent. So we need to figure out what type of shape these have. The electron groups and the shape. So we have PF3. This is phosphorus difluoride. We have water, and we have carbon tetrachloride. So we've got to figure out what these are. So I put them all in one page. I'm sorry if this looks busy, but it's the easiest way for me to explain them. We always draw the Lewis structure. So I jumped ahead and pretended that you drew a Lewis structure. You figured out the valence electrons, you plugged it in, and now you're going to take a summary of everything you have. So here is phosphorus trifluoride. We have 4 electron groups, 1, 2, 3, 4. We have 3 bonded and 1 lone pair. So we're going to take a look at the chart. I think I put the chart here. And so we have 4 electron groups, 3 bonded, 1 lone pair, and this gives us a shape of trigonal pyramidal. And what you don't see is there's a lone pair here. So let's see if that's how it looks. What happened to it? Oh, I guess it's not actually asking for the rest of it. It just wants to know the shape. So use the atoms bonded to the central atom, determine the molecular shape. And so it wants the shape, actually, not even the electron group. And it's trigonal pyramidal, which is what I just covered, but I'm going to cover both of them, the electron group and the shape, so you understand. Next one is water. Water has 4 electron groups, but it wants to know the shape. So we have 2 pairs, 2 bonded and 2 lone pairs. So we go back down to 4, 2 bonded, 2 lone pair, 109, and the bent shape is bent. And that's what you see here. It's drawn with the lone pairs here, pushing these down towards each other because there's greater repulsion going here with the electron pairs, lone pairs. And now we have carbon tetrachloride. This is very symmetrical. They're all matching. We have 4 electron groups and no lone pair. And that means that the electron group name and the shape name should be the same. So here we have 4, 4, 0, 109, and tetrahedral. And here it is. Even though this is with hydrogens, this is the shape of it. It's a tetrahedral. Okay, now we're going to get into the polarity of molecules. The shape determines if polarities exist or not in molecules. You can have a molecule that has polar bonds, but the bonds will cancel out based on how the shape is. And then overall, the molecule will be non-polar. So that's what we've got to learn here. And this is a little difficult for people to understand. And a lot of it is just looking at it and trying to determine where the electron negativity is going. And if you can see a gap where it's not being pulled evenly, then the molecule is polar. All right, so matching molecules, H2, Cl2, O2, they're all nonpolar. That's a tug of war that's never going to happen, so we don't have to worry about those. They cancel out. Same thing for carbon dioxide. This cancels out because we've got symmetrical end atoms, and they're just pulling it. It's nonpolar. They're going to cancel out. So even if these bonds are polar, there's a tug of war that's happening, never going to change. Now we look at carbon tetrachloride. Carbon tetrachloride, even if there is a dipole here, meaning a polar, there's a separation of charge where the chlorine is pulling more of the electrons away in the bond than the carbon. There's 4 of them, and the shape is tetrahedral, so it's very symmetrical. And even though you can't really see it here, because what it's doing is it looks like it's sitting on like 3 fingers and then 1 up, if you're trying to do it with your hand, kind of. What this is that there's four electronegativity forces being pulled in 4 opposite ways that actually cancel out. Like I said, this may not look like it's canceling out, but the forces are all equal and they're canceling out. So even if it was a polar bond, it is a non-polar molecule overall. Not all of them are. HCl, this is a polar molecule. This doesn't state the difference of it, but we're going to just say this is a polar molecule. Cl has more electronegativity pull than the hydrogen, and it's a polar molecule. There's a separation of charge here, and nothing's there to cancel it out. Polar molecule. Water is a polar molecule. I'll just tell you that right now. It is 2 lone pairs, 2 bonds. There is, as you see, the hydrogens, the electronegativity is all being pulled by the oxygen, meaning that there's an imbalance here on the overall molecule, and this creates a polarity in the water. And it makes, see the arrows, this is partial positive, this is partial positive, this is partial negative. Okay, so now we're looking at ammonia. Ammonia has a nitrogen with a lone pair on it and hydrogens around it. And again, it's the same thing. It's pulling all the electron density towards the nitrogen. And this is also a polar molecule because there's not an equal pull in all directions like there would be with the carbon tetrachloride. So this does not cancel out. There's an imbalance. And this is a trigonal pyramidal, so it's all going towards the top if you think of it as a pyramid. Okay, so let's determine whether a molecule of OF2 is a polar or nonpolar. Okay, so first thing you need to do is you need to draw it out. Or you can determine the bonds. So there's 2 ways. Sometimes you're going to have to go further. So you can either first try to do the subtraction with the actual numbers that would be given to you. You would be given those numbers. Or you can draw it out and try to visually determine it as well. We know that fluorine is the strongest of electronegativity. So it's a 4. This gives us a difference of 0.5 for each bond. So this is 0.5. It's in the range of polar covalent. Now, step 2, if the bonds are polar, you need to draw it out because you probably are going to be asked to draw it out and you're going to be asked to show where the partial positive is and where the partial negative is. So in this case, fluorine is being pulled, the electron density from oxygen here is being pulled this way, and then another set is being pulled this way. So this is very partial positive over here. This is very partial negative, partial negative. There's an unbalanced pull on this. It's not linear, so it's not being spread across, and not all the forces. This is very positive here, this is very negative, so it's just not balanced at all. It's going to be an overall polar molecule. And this is where it's hard to envision, so use the arrows if you need to. use the delta if you have to draw it so you can see that there's not a balance of forces being pulled in all directions that will allow it to cancel out. Identify each of the following molecules as polar or nonpolar. So the first one we have here, we have PBr3, we have HBr, and we have CH4. So first things, the numbers here have been supplied, so we've jumped ahead again because this is turning out to be a very long lecture, and I try to keep my lectures, shorter than this for you guys, so I don't lose you in this. So phosphorus is 2.1, bromine is 2.8. It gives an overall of 0.7, so that makes it polar. Same for HBr, gives an overall of 0.7, polar. And methane gives a nonpolar because it's 0.4. Remember, the range for nonpolar is 0 to 0.4. It's asking to see if you can draw it out. So we don't necessarily have to draw this one out, but it is anyways. It's a tetrahedral arrangement. And even though it's kind of hard to see here, but these are being pulled in all 4 different directions. So even if it had, since they're all the same end atoms, this would still be nonpolar because they're all being pulled in 4 different directions equally. There's just one bond. That's an easy one. There's one side that's going to pull it and nothing's going to be able to control it on the other side. This is a partial positive. This is a partial negative. And there's no other forces to cancel it out. So it's polar. These are a little harder to understand, but just remember you have a lone pair here, and the lone pair makes this all uneven because you have 3 bromines in pulling one direction, but you also have now a lone pair that's pulling as well, or trying to pull. And so because of that, so the bromines here, you see it's 2.8, 2.8, 2.8. So you have 3 pulling in 3 different directions, but this is now leaving this partial positive because a little bit's going here, a little bit's going here, and a little bit's going here. This makes it partial positive, and then you have negative, partial negative, and that makes this a polar molecule because the forces are not canceling out evenly. And that's it. Thank you.